So we have obtained the following solution of the Einstein equations: 1 minus rg divided by r dt squared minus dr squared 1 minus rg divided by r minus r squared d omega squared. So this solution is where rg is equal to kappa m, and m is the mass of the gravitating center. So this solution describes spherically symmetric gravitational field of this sphere. And let us describe what type of observers see this metric. Well, I already say that this metric is invariant under time reversal and time translational invariance. Its components are time independent. And so this metric is static. And if we consider time slices of this metric, time slices of this metric are sliced as onions, as spheres. The spheres have the following radii. So the radii of the sphere as, well, the distance between 2 points, R1 and R2, is given by dr divided by square root of 1 minus rg divided by r. And it is not equal to R2 minus R1. It's only approximately equal to this value if we are very far, if R1 and R2 are much greater than Rg, then there is an approximate relation between these two quantities. So they are not equal. This is important, and this is again that the radii of the spheres are different. So this would be the radii if we would integrate anyway. So the radii are not directly related to the areas of the sphere. That's the first thing. And then let us look at the observers. So consider someone who doesn't move in spatial directions. So consider this: dt d phi is equal to 0. So the static observers in this metric. Static observers of this metric, so their world lines are just t, 0, 0, 0, and they are fixed at a given radius, at a given angles over the gravitating center. So there is a gravitating center, and these guys are fixed at a given radius and given theta and phi. So these are non-inertial. So we say that this Schwarzschild metric is seen by non-inertial observers which are fixed above this gravitating center. This is important. And let us describe properties of this metric in greater detail. One can easily see that this metric degenerates as r goes to rg. As r goes to rg, this metric degenerates. So this component goes to 0, while this component blows up, goes to infinity. So, but this is not a physical singularity. This singularity is very similar to the one we have encountered in the first lecture for Rindler. For the Rindler metric, there was a singularity at r equals to rho equals to 0, which is similar to the polar coordinate singularity at r equals to 0. So this singularity of this metric at r equals to rg is similar to this sort of singularities, so it's unphysical. The way to see it, to consider invariance. So for example, let us consider, we're going to show that there are no invariants of the metric that blow up. I mean, invariance of the under general covariant transformation invariance. So we're going to build up invariance of the metric, and we're going to see that they don't blow up. So the simplest invariant that one can build is the volume form. So this invariant for the given metric, as one can see, this factor and this factor in this invariant cancel each other. So this is a determinant of this metric. And it is equal to r squared sine theta dr d theta d phi. So it is regular. That's the first thing. Then one can, for example, study components of a Riemann tensor. Components of the Riemann tensor, of course, have various singular properties. So, for example, this component of the... So let me write all the non-zero components of Riemann tensor. One of them is like this. The other one is related to this one by the sine squared of theta, and equals to minus rg r minus rg 2r squared, and r12 equals to r13 divided by sine squared theta. This is equals to rg divided by 2r minus rg. So this component of Riemann tensor is singular at r equals to rg. R23 is equal to minus rg r sine squared theta. But let us look at invariant. Invariant, for example, simplest invariant would be r, but it is 0 because r mu nu. So because r mu nu is 0 for this metric, then r is 0 also. So this is the simplest invariant. But then let us construct invariant from the Riemann tensor. The simplest invariant that one can construct like this. And it happens to be equal to 3rg squared divided by r to the 6th power. And this guy is completely regular at r equals to, as r goes to rg, this guy is regular. So this way one can build many different invariants from these guys, and all of them will be regular at this point. It means that this singularity is the coordinate singularity. So it's similar to this singularity for Rindler space that we have encountered in the first lecture, or this singularity in polar coordinates, two-dimensional polar coordinates, that we have also discussed in the first lecture. So there is another way to see that there is nothing horrible happens at this point for this metric, and we're going to discuss it now.